how we deal with kind of an extreme situation. So we've got, we talked about drag force yesterday, right? Drag force, we know it's force exerted when an object passes through a fluid, right? There's some things about it that I think when you look at it, just makes sense. We know that it's going to be proportional to the drag coefficient, right? So the shape of an object has a lot to do with it, right? The sleeker, the more aerodynamic, more streamlined the shape, the smaller the force due to drag, right? Drag force. It's also proportional to the fluid density. The denser the fluid, the greater the drag it's going to create, right? It's proportional to area. The greater the cross-sectional area, the greater the drag. And it's proportional to the square of velocity, so it's especially sensitive to velocity, right? If you double your velocity, you're actually quadrupling the drag force. Okay, you're going to do your let me say, we're going to do your ping pong paddle experiment over the weekend, right? Okay. So that's drag force. We looked at some examples of that yesterday, didn't we? I think we did skydiver, right? Figured out what my terminal velocity would be skydiving. We looked at, did we look at anything else? We started to we talked about cars a little bit. And you can see here's some coefficients, some drag coefficients for various different things. And then what I want to look at today, we talked about how there's kind of a line that we cross at some point where if an object is small enough and light enough that this doesn't really work anymore, right? And some examples, we kind of talked about how, a mouse seems superhuman in that a mouse, you could drop a mouse out of an airplane and the mouse would survive. It'd be fine. I mean, it might not enjoy it, but it's probably going to walk away from that, right? But it's not a person, not a big animal, right? But a bug, oh, obviously no problem. Wouldn't even notice it. If you dropped a beetle out of an airplane, it would be fine. It wouldn't even, seriously, probably wouldn't even notice that it had hit the ground. It would just walk off. And why is that? Okay, this has to do with, we kind of started to talk about it a little bit, but physics doesn't work the same on all scales, right? I can't remember if we talked about this before, but this is kind of interesting.
Just a little bit.
Physics kind of ruins, it sort of ruins sci-fi movies for you just a little bit too. I hate to say that, but you're going to look at it, you'll look at it and go, oh, that can't happen, and you just got to go with it sometimes, I suppose. But something like King Kong could never happen, right? How come?
Which part?
The big gorilla part. You could never have a huge gorilla. You could never have, it'd be like ones I saw when I was a kid, some stupid movie where ants got really big, right? Ants were like 6 feet tall. Could never happen. None of that stuff could ever happen. How come?
I've heard the ant thing, how their density would stay the same, but if they got bigger, then they'd float off because they're so.
Well, an ant couldn't even, I mean, it wouldn't even be able to.
Their mass.
Yeah, it would. I mean, it couldn't stand up. Nor could probably King Kong. Probably couldn't stand up. Well, how come? What's going on? I think
like a proportionality of the body to the bones.
It keeps growing.
Like it's going so much faster that the bones would not be able to withstand it.
Okay, so well, everything would grow proportionally, but think about this: is an object's mass going to be proportional to its height, its surface area, or its volume? And everybody just think about that, because everyone can answer that. I just want to think about that for a second, though. Is an object's mass proportional to its height, its surface area, or its volume? Object's mass. What is the definition of mass? The amount of matter in an object. So it's got to be volume, doesn't it? It's got to be volume, right? So if we scale up a gorilla by a factor of, I don't know, how many times bigger is King Kong than a gorilla? He's like 50 feet tall or something.
Which version?
Yeah, which version? So if he's 50 feet tall, that's probably like 10 times maybe, the 10 times scaled up. So that means 10 cubed is what? 1,000. So we're increasing his mass, therefore his weight, by a factor of 1,000. Okay. What's happening to here, here. Thanks. Okay, so what about his ability to support himself? What causes us to be able to stand up? What's providing the structural support for us when we're standing up?
Skeletal system.
Our skeletal system, right? Okay, and this is kind of some new physics that we'll talk a little bit about in the future, but it's our femurs, for example, right? They've got to be able to support in our, tibia and all, the bones of our legs have to be able to support our weight. Turns out that this is a kind of a statics problem, but if you want to look at the ability of a material to support weight, it's proportional to the strength of the bone, for example, is proportional to the cross-sectional area of the bone. So if I cut through the bone, the cross-sectional area determines how strong it is, right? So then, if we're going to scale up King Kong by a factor of 10, how much is the cross-sectional area of the bone going to increase?
100.
Not 10, because it's an area.
1,000.
1,000. Well, not 1,000, sorry. 100, 10 squared, right? Because it's an area. If we're scaling up height by 10, that means an area is going to be scaled up by 10 by 10, right? So it's going to be scaled up by 100, and a volume scaled up by 10 by 10 by 10 by 1,000. So King Kong's, the gorilla's ability to support his weight is only increasing by a factor of 100, but his mass is increasing by a factor of 1,000. His mass is increasing 10 times faster than his ability to support himself, right? So at some point then, it's not going to work, right? At some point, you're going to grow to the point where, I don't know what the engineering factor that, evolution is built into all this. I don't know how much force our bones can support, but it's not unlimited, right? So maybe we can support, maybe we can support 15 times our weight or something like that. Who knows, right? But when you take a step or you jump up in the air and you come down, you're multiplying the forces on your bones quite a bit. So there's going to be a point where an animal that was just scaled up might be able to barely walk around, but as soon as it took a big step, it would break its leg, right? Because the forces would multiply past that threshold force. So it wouldn't work, right? See what I'm saying? And so, yeah, it doesn't work. Scaling things up and down doesn't work. Same thing happens, like fleas are superhuman, right? They can jump, hundreds of times their height. How come? Well, because they're so small, right? We could never do that. We could never generate those kinds of forces in our tissues, but they can. You could never build, a mountain could never be 100 miles high. It couldn't be 100 miles high because the structure of the mountain, the rock, would never support it, right? It would just fall down. So it's, the scale, you have to be careful when you try to scale things in physics. So things change when you go to very, very small scales. When you go to very small scales, this is no longer, the model that works for us. This is the model that works for us instead. We call it Stokes Law. That's it. Okay, so it tells us that now, we call this F sub S, for Stokes force. But this is just going to be essentially like the resistance force when you're passing through the fluid. Yes, ma'am?
What made dinosaurs possible?
What made dinosaurs possible? Because they're so big?
Yeah.
Okay, good question. If you look at the physiology of a T-Rex, T-Rex does not look like a person. Think what a T-Rex, I'm not a very good artist, but if I were to draw a T-Rex, it looks something like this, right? There's the head, big teeth, right? And then it comes down and it kind of goes, got a big tail, and then its body kind of looks like this, and then its legs would be, that's a pretty darn big T-Rex, isn't it? You get the idea. Its legs are huge, proportionally, right? Huge. That's not the way a person looks. The legs on a person, they represent less than half of our mass, for sure. But on a T-Rex, they would represent the vast majority of the mass of the T-Rex would come from right there. Everything else is pretty small, right? And the tail's probably a little too big. But the tails are there to help them balance while they're walking.
What about a giraffe?
What about a giraffe? Okay, giraffes aren't super massive. I mean, giraffes are like, the mass of a giraffe is not that incredibly different from like a draft horse, right? Like a draft horse. They're taller, but you know what I mean? And so if you look, and that, if you looked at the cross-section of the bones of a horse, they're big. I mean, they're really big, right? So they're built to support lots of weight. But a T-Rex has to support all that mass, and so its physiology is totally different. It's got to have much beefier supporting members here, right? The legs have to be a lot bigger because as the weight increases, the area has to increase more than linearly with the height, right? See what I'm saying? And so when you look at those really big dinosaurs, yeah, they've got huge, look at like a brontosaurus or something. I mean, their legs are enormous. Most of them are huge. Look at an elephant. Legs are enormous, right? Yep. Oh, yep.
What about like ostriches and eagles and stuff?
Okay, because they look like they have such skinny legs. I mean, yeah, but ostriches, how much does an ostrich really weigh?
Like 40 kilos maybe.
Not that much. Yeah, really not that much. They're where are their muscles too? Their attachments are a little different, right? And you can even see that there's some variation among people. Like people that can jump really high, a lot of times if you look at the physiology of jumpers, their attachments are higher on their bones. Like if you look at a guy that can really jump high, his calves are always going to be pretty high. It's very rare that you find somebody with elongated calves that's going to be a really good jumper. It just doesn't work. And that's because they can jump really high, yeah. And that's the same way it is like with animals. A lot of times animals, they'll have the what do you call it, the belly of the muscle isn't actually in the leg, it's going to be up higher. And there's just a lot of tendons and things that transmit the force that are going through their skinny legs. Like with a deer too, same thing. I mean, deer can weigh as much as a person, but they can just jump over a big fence. How come? Not because their legs are so beefy, but because they've got really strong muscles that attach to the hips, and it's right. So they got bigger muscles, but they're just not on their legs. The force is just transmitted via tendons and ligaments.
I looked it up, I think we have to like 150 to 100 something kilograms.
Right. So that's like a person, right? Like a big person. Big person, right? Like a and the thought is that ostriches look like they're so spindly compared to a person, but they're not. I mean, their bones are probably, ostrich probably has the same size bones as a person. And they're going to be a little different composition, right? They're going to be, they're not going to have as much, like a cross-section of a human long bone would have a lot of, have a lot of different types of osteocytes. It's going to have some that are going to be, what do they call it, porous, what's that kind of bone called? Anyways, a bird, if you look at the cross-section of a bird's leg, it's all fibrous bone. So they're a little different composition, but then the muscles just aren't on their legs. They're up higher. They're going to be in the body of the bird, right? Think about when you eat a chicken. Where's the muscle? In the legs. It's up in the body, right? So it's not really on the leg as much. Okay? So yeah, I mean it's different. Just reading things.
So when are we going to use this one?
Okay, so then this one. So this is a different law, right? So this is what works for really small things. So what is this? So the force now, right? The fluid force that's exerted on really small objects, it just turns out it's equal to 6 times pi. And we always assume, notice r is the radius. So objects that are really small, we're always going to model them as spheres. They may not be, but that's how we're always going to model them. We're going to come up with some effective radius. Times, this is called eta, and eta represents the object's viscosity. Okay, we'll pull up a table of viscosities in a second so you can kind of see how they vary from fluid to fluid, times speed. Okay, so let's look up real quick. I'm just going to Google viscosities over here. We'll see what we get.
So Stokes, this is just for
Stokes Law for very small objects. Like we're talking about microorganisms. You could talk about like protozoans and bacteria. For dust particles, really fine dust particles, particulates in the air, smoke, things like that, soot, that kind of stuff, really small stuff. Grains of pollen. All right.
Yeah, it's like
See if we get a little table of viscosities here. And there's all kinds of different units we could use to here's just these are kind of weird units on these. A lot of times you get these bizarre units. We're going to talk about ours in standard units, but molten chocolate, how about that? That's,
What temperature?
that's, yeah, I don't know. Some planet, some candy planet, that's what the volcanoes spew out is molten chocolate. So look at the viscosities here. This is going to be a weird way of describing the units, but you can see the relative sizes. Like blood has a viscosity of 3 to 4. Well, look at the viscosity of molten chocolate, 45,000 to 130,000. What's that telling you? Really thick. Exactly, it's really thick. So an object, like if you were to drop a ball bearing into, you know, it's kind of gross, but if you dropped it into a vat of blood, it's just going to go right to the bottom, right? But what about molten chocolate? Well, molten chocolate, it's going to take a long time. It's going to go very slowly through that. Or through, I mean, typically you think of molasses as being really thick and viscous.
Through peanut butter.
Ketchup, oh, look at peanut butter. Oh my gosh. Shortening. How about glass? Glass is a fluid. Glass is a fluid. It actually does. Have you guys ever been to a really old building? Yeah. If you've been like in Europe, when I was, have you ever been to?
Oh, and it like it'll leak down the window.
Yeah. You don't see it as much in the U.S. because the buildings aren't old enough. But if you go to Europe, you can see some of these really old windows that are many hundreds of years old. If you look at the bottom, they get real thin at the top and they get thicker at the bottom, and it actually distorts the light a little bit because the glass has literally flowed. I mean, you can treat it as a very viscous fluid, and it's literally just flowed down the surface.
Is there an instance where it started to like turn away?
I don't know. I mean, I would think at some point probably, you know, you'd probably have things like even just a little wind would crack it and stuff. So that's a very good question. I don't know. But at some point it would. Yeah, at some point it's going to pull away. It might take a long time though. It might take longer than windows have been around because there's going to be a surface tension there's some other forces going on that's going to make it really hard to finally pull it away. But they get pretty thin.
So that is molten glass viscosity, okay? But if you put like a ball bearing just on like a glass tabletop or something and left it there for hundreds of years, would it eventually?
Well, okay, not really, because a tabletop's not a fluid. Yeah, fluid's different, and we'll talk later on when we get to that part of physics. We'll talk about what it means to be a gas or a liquid and gases and liquids can both be fluids, right? But a solid is not typically. A solid, if it's got some structure to it, a lot of times it's not going to deform very
Even
much.
if it's glass.
Yeah. Well, glass, it depends. It depends what kind of glass.
A glass sheet. And you put
Like
it
on those coffee tables.
yeah, and you let that run.
If it's, okay now, and I don't know, you know, I'm not an expert on glass, but when you go through the process of like tempering glass, I think you do some things to the structure of the molecules in the glass that turn it into something that really doesn't resemble a fluid anymore. The old glass that people, like in the old days, the glass was different. It wasn't, now we have modern techniques of producing glass that produce better glass that's stronger, that's more stable. But in the old days, that's not how they didn't really have the capability. And so their glass was just kind of, molten glass was just sort of, you know, stretched out. And I mean, you know, it was difficult to make. You could pancake it, but it's like when you draw steel. There's a documentary you got to watch. And this, I know this sounds like it's going to be interesting, but it's really interesting. The Nova about the Viking swords.
Oh, I saw that one.
And that's a good one. They talk about the process that they used. They actually could produce this crucible steel, which really hot steel, and so they could heat this stuff up to get out the impurities, and then they keep on hammering it and drawing it. And when you go through that process, it creates much stronger steel because of, and it, you know, it'll keep an edge. Whereas if you just take, you know, iron, you try to make just cast an iron sword, it's going to break almost instantly. because the molecules aren't aligned properly to be strong, right? You want to smear them out over, so they have sort of an orientation on a molecular level, which you get by going through that process. Same thing with glass. You can align the molecules in the glass so it's much stronger. I don't know if that would get talking so much about glass.
Isn't that kind of how like diamonds work? Like they have a grain?
Yeah, now diamonds do. Diamonds, you can't, diamond's a crystal. Crystals are not fluids. Crystals, they have very strong molecular bonds which hold the shape. I mean, diamond's hard. If you look on that Fresnel scale for hardness, diamond's right at the top. So diamonds can scratch anything, essentially, right? Because they're so hard. They're crystals. The crystals hold that lattice of molecules in place. It's very difficult to displace those molecules. They'll spring right back, right? They're not going to flow. Whereas water flows because the bonds between the individual molecules are very weak, right? So the individual molecules, it's like if you have a pot full of BBs, the BBs can shift around, right? But if you were to pour some glue into that pot full of BBs, they wouldn't shift around anymore because now they're glued together. See what I'm saying? And so a true solid, is going to be a non-fluid. And we divide, I mean, as you go further in physics, you'll divide fluids up into Newtonian fluids and non-Newtonian fluids. There's all kinds of variations as you look at it more and more closely. But essentially, if you've got a true solid that's not a fluid, those particles are held in place rigidly. They're not going to move, right? They can't. They can't freely flow. And that, ultimately, that has to do with, the chemical bonds, right? The nature of the chemical bonds. Okay? But, so you get an idea. I mean, there are vastly different viscosities. So let's look at maybe an example of a problem we could do with this. This is kind of interesting. So I just love the fact that you can answer questions about the world with physics. I mean, we can really take something. Well, you can too. Where's
We
my?
can answer questions about a sled.
So if we go down, I'm just going to go to our textbook. I think there were some pretty cool questions in there. Yeah, right here. So if we go down,
World's foremost sled.
how about this, right here? Find the terminal velocity of a spherical bacterium. So think about that. You got a tiny, what is that little symbol right there? Not nano. Micro. Yeah. So a micrometer, what is that?
Really small.
Really small.
How small?
A thousandth of a millimeter.
Thousandth of a millimeter, so it's a millionth of a meter. Micrometer, it's 10 to the minus 6 meters. So that's small, right? You're talking about a bacteria here with a diameter of 2 millionths of a meter, right? So the radius is 1/1 millionth of a meter. That's tiny. If it's falling in water, I mean, it's almost difficult to think about that, of something that small falling in water, because most of the water we ever deal with is not still, right? There's going to be currents, whether they're convective currents, where there's the hot water is rising, there's a little temperature gradient in there, and so there's always a little bit of mixing. But if you had truly still water, like under a glacier or something, where it's just all the same temperature, and there's no vibrations, then that's what you'd almost need for something like this to fall through there. Every little tiny bit of current would be like us walking into a Category 5 tornado, right? It's going to just zip that thing around. Okay, so if we want to come up with its terminal velocity, and we know the density of the bacterium, okay, we can find, for water, we can easily find its viscosity. That'll just be on the table, right? We can pull that up in a table. So we can do this, right? How would we go about this then? If we want to do a problem, let's just grab that problem. Oh, lost it. Where'd it go? Right there. There we go. Okay. And let's make the writing a little bigger. Oh, no, I lost it again, though. There it is, right there. Okay. Oh my gosh. This is so complicated, all this technology. There we go. I can get rid of all that stuff. Okay, there we go. So we want to find terminal velocity. Well, if this is the resistive force, right? What are the forces acting on the bacterium in the water?
Gravity.
Gravity's pulling them towards the center of the earth, right? What else?
And that force.
Yeah, that force.
That's
right?
it.
Okay, that's it. So if we want to come up with terminal velocity, all we've got to do is set Stokes force equal to mg, right? So 6 pi r eta v equals mg, and we're just solving for v, aren't we? Right, that's no big deal. So v just equals mg divided by all that stuff. Okay, and what do we know here? Okay, so we don't have the mass of the bacterium. How are we going to get it? We have density, don't we? Good. So we know that the density of the bacterium is that, right? Well, density is what? Mass divided by volume. Okay, so m divided by volume, and it's a sphere, right? We're assuming it's a sphere, spherical bacterium. We know the diameter. So what's the formula for the volume of a sphere?
Was that 4/3 pi r cubed?
4/3 pi r cubed. So m divided by 4/3 pi r cubed equals density, which is that, right? So if I want to solve for, I need to solve for m, don't I? Right, so then m, if I just multiply both sides by that, m just equals volume times density. So let's pull up the calculator and do that. That's just calculator. So what do I got here then? I want 4/3 times pi times r. So
1.
yeah, so if the diameter is 2 micrometers, what's the radius? 1 micrometer. Okay, so that's going to be 1 times 10 to the negative 6.
What?
1 micrometer is 10 to the 6 meters.
Oh.
10 to the negative 6 meters. So 1e negative 6. Okay. Cubed. I guess I better put that in parentheses. Cubed times the density of, that's in standard units, isn't it? 1.1 times 10 to the 3, so that's about a little over, it's about 1,100 kilograms per cubic meter. If I filled up a cubic meter with solid bacteria, it would have a mass of over 1,000 kilograms. That's a lot of bacteria.
You're gonna have to find a lot.
Okay, oops. Times 1100. I'll just write it like that. Okay, so that's our mass, and the mass is small. That's it. 4.6 times 10 to the negative 15 kilograms. Zoinks, that's small. Okay. So we got mass. What else do we need to find our velocity? So we got mass, we know g, we know 6 pi, we know the radius, but we don't know this, the viscosity of water. That's all we need though, right? So we'll just look that up. I bet that's even in this table right here. Probably wrong units though.
I think it should be about 1.
What units do we need?
I wonder if it's in, I bet it's in our book, huh? If I go to the book here, let's see. Oh, where is it? Do we get any?
What's the standard for viscosity? Is there a standard unit?
Well, okay,
Like
you
if they're
guys can
one.
tell me what the units are. Look at, if I pull up, okay, you tell me, go away. what are the units going to be for viscosity? If that's viscosity, right? So viscosity, if I solve for viscosity, what am I going to get? If I isolate eta, I'm going to get force divided by 6 pi, that's unitless, R V. Okay, so you tell me, you think about that while I find the viscosity of water.
Meters squared per second.
No.
Would be Newton's times seconds divided by meters squared.
Say it again.
Newton's seconds divided by meters squared.
Okay, yeah, we can simplify that more though. What are the units of Newton's going to be? Think about Newton's second law.
Kilograms per meter per second squared.
Kilograms times meters per second squared, right? Because mass times acceleration. Okay, so now go back to work on that. Tell me what the
Oh.
Kilograms per second.
almost close
Kilograms per meter.
kilograms.
Per
No,
Kilograms per second.
close, close.
Kilograms per meter.
Very close. You're missing one
Kilograms per
thing.
meter second.
Kilograms per meter second. That's it. That's it. I'm having a heck of a time finding
Can't just Google
viscosity. Yeah, I'm gonna do that.
That might fail ya.
There we go. Viscosity of water. All right. Water viscosity table. Here we go. Here we go. Okay, so we want probably low temperature water. So we'll just take it at 2 degrees Celsius. So this is going to be in grams per cubic centimeter. So I'm going to multiply by 1,000. So it's going to be, it's about, just a little less than 1. So we'll say it's going to be about 1,000. 1,000 kilograms per cubic meter. Okay, we'll say that's the, hang on, that's the wrong, that's density, not viscosity. I want kilograms, kinetic viscosity, dynamic viscosity. Man, this is harder than you'd think to find the right viscosity. How do they not give us that in the textbook? Well, that seems like that's something you ought to just have. And I don't honestly know what it is.
I guess it's about one.
Viscosity of water. And there we go, kilogram, that's what I want. Oops, right there, kilogram meters per second. There we go, okay. It is about, somebody write this down, 0.001002. And that seems right, it would be very low.
How many
Okay.
zeros?
0.001.
0.002.
Yeah.
2 zeros and 1, 2 zeros.
So, we'll write that down. And then the units would be kilograms per meter times second. Okay, so let's plug that in, and we'll see what the terminal velocity is. How fast do you think this bacterium is going to go?
Not very.
Not very fast.
Okay, so terminal velocity is m. That's our m, right? So we've got m times g. Okay, so there's the numerator divided by the quantity, 6 times pi times r, which is, what was it, it was 1 micrometer, right?
1 e to
And so 1 e negative 6 times eta, which was this number.
0.01002.
0.00102. Okay. fast?
No.
What do you think?
2.39.
Pretty slow. So this thing is moving about 2.4 standard units, about 2.4 times 10 to the negative 6 meters per second. So it's moving at about the blazing speed of about 2.4 micrometers per second would be its terminal velocity in water.
2.4
That's
millions
nuts.
of
Yeah, so how long is it gonna take to go a meter?
Years,
A long
2
time.
million seconds.
centuries.
It's gonna take, I mean, it's gonna be, well, what's a million divided by 2.5? So it's gonna take a lot of seconds to drift a full meter in that water, all full meter.
By
So-
that time, it's probably gonna move.
So what do you think then, what have bacteria evolved to be able to do? Yeah, they've got flagella, they can move, because they won't drift very far, right? In still water. Okay, how much time?